Thanks, Judd. And thanks everybody for joining today. As Judd stated, I'd like to give a very quick overview of groundwater nitrate in Wisconsin, and then talk about some of the things that we're seeing in our monitoring efforts in central Wisconsin. Try to put into context the nitrogen loss component of agricultural systems. Just briefly, I see our nitrate challenge, particularly in the central sands, as being a focus on that top foot. Maybe that's a little dramatic, but what we know is that current agricultural systems allow for significant nitrate losses to groundwater. I think I'll show some information that shows much of it can occur outside the growing season. So I really see this as a year-round issue, not just a growing season issue. We know soils and geologic considerations exacerbate losses from these agricultural systems. So the sandy soils in central Wisconsin, other irrigated regions where we do a lot of vegetable crop production are particularly vulnerable. And then also climate change will impact nitrate losses. So moving forward, if we consider more extreme rainfall events, longer growing seasons, increased soil temperatures, all those things have implications for nitrogen budgets and nitrogen management. When we talk about nitrate in groundwater, it's particularly relevant to Wisconsin just because of our reliance on groundwater as a drinking water source. 95% of Wisconsin communities rely on groundwater or municipal wells, and about 35% of all Wisconsin residents have private wells that they use at home for their drinking water. When we look at background levels of nitrate in groundwater, we'd typically say less than 1 is what we'd expect if we didn't have agricultural activity, if there were no other sources of nitrogen to groundwater. Think forested regions, grasslands, prairies, we'd expect the groundwater concentration to be less than 1. When that concentration exceeds 10 milligrams per liter, that's the drinking water standard. And then there's some guidance or some precautions that people have to take if they're using that water source for their drinking water. So that's kind of the magic number in terms of public health, where we start to get concerned. Groundwater is connected very intimately to surface waters, so that nitrate exported to surface waters from groundwater can be important for Gulf hypoxia issues, but also blue-green algae blooms are increasingly thought to be associated with excess nitrogen in surface waters. If we look at nitrate occurrence in Wisconsin, what we can use is well water data, because you can pretty much drill a well anywhere in the state of Wisconsin and access water. Our development pattern means that you can pretty much put a home anywhere in the state and get accessible water, ample water. So this map shows what we know from hundreds of thousands of well samples. It's a little extreme because the highest or most extreme value is always mapped on top. So it doesn't mean that in those areas where you see red that you can't get good water. It just means that those are areas where there's wells that have higher concentrations. So the other way we can look at this data is to aggregate it. And that's where a tool available online called the Wisconsin Well Water Viewer comes in. It basically averages out that data, that private well water data by town range. You can even go down to it at a section level, but it creates a nice picture. Those areas in white are areas where we don't have a lot of wells and don't have a lot of data. But those other areas, the color gradient corresponds to the concentration of nitrate from low, none detected, and the lighter yellow to the darker red, which would mean higher concentration. Some areas where the average concentration might be greater than 10 milligrams per liter. How to explain these patterns? We can look at both the land use as well as the geology, and agricultural activity has a strong correlation to areas where we have elevated nitrate. In those areas where we have a lot of sand deposits or sand and gravel as the primary aquifer, those areas really stand out. And then eastern Wisconsin, areas where you have the Silurian dolomite and very thin soils are areas that also stand out as being particularly vulnerable. So it's really the combination of land use and geology that determine where we find nitrate in Wisconsin's groundwater. Those sandy areas are also obviously the areas where we have a lot of irrigated agriculture, which makes growing high value crops much more productive or more successful. So that's why kind of we're here today, is to talk about some of those issues that might result from the types of activities we find here. If we want to look at trends, there is some data that we have on public water systems, which are required to test for nitrate annually. If we look at that data, it provides a 10 to 20 year record where we can start looking at trends over time. More than probably 10,000 wells are a part of that data set. If there's good news, it shows that the vast majority of wells don't show any significant trend. However, roughly 10% of all private wells statewide exceed the drinking water standard. So the fact that they're not changing might be good news, but it doesn't necessarily mean that there's not significant numbers of wells that are impacted with respect to nitrate. And in those wells that are increasing or are showing a trend, there are more wells increasing than decreasing. And that's what the map on the right shows, is just those wells in pink or kind of the darker pink or reddish color correspond to wells that are increasing, and the size of that dot corresponds to the magnitude or the size of that trend, the rate of change in those particular wells. So while groundwater isn't, we're not seeing things change dramatically, we do see parts of the state where things are changing, and generally, more often than not, they're changing in what we consider to be the wrong direction. Getting to the agricultural component of this, obviously nitrogen is important for yield, and the yields we're getting is partially a function of how much nitrogen is added, and that's what I'm sure a lot of you focus on, is getting the most out of your field, getting the most profitability out of your field, and maximum yield isn't always the most profitable, because eventually there's a point where you're paying more for the fertilizer than you're getting back in terms of profit from that additional yield. So economic optimum is something that you all think a lot about, but what I tend to think about is what is the impact of those practices on the groundwater system. So that's what I'd like to focus on in the next part of the presentation, is basically looking at data I've collected in the Central Sands from the standpoint of how much is actually getting into the groundwater. And that's where using kind of simple nitrogen budgets can be effective. There's a paper from back in 1991 that really outlines a very good approach to doing this. It contains a lot of great literature values where we can estimate nitrogen content in harvested portions of our crop. If we know the other inputs like fertilizers, the water, the nitrogen that might be coming from irrigation water, we can get a pretty good handle on the inputs. If we know the harvested biomass or the yield, that's going to be the bulk of the outputs. In the sands, we assume that change in storage is pretty negligible from year to year. So by looking at the inputs and subtracting the outputs, it gives us the ability to estimate the potential leachable N. And then if we have that number, we can compare it to data on water quality to see if this simple approach gets us in the ballpark and starts to help us understand where we might be able to see improvements. So I'm going to just briefly transition to an Excel sheet. And I think the Excel sheet is nice. And John, I see you in my screen. Can you see the Excel sheet? Thumbs up. Thanks. This Excel sheet, just allows you to kind of tweak things a little bit. So right now it's set where all our inputs and outputs are zero. But if we look at this bar here, I'm going to set this to sweet corn. If we assume a yield of 8.5, that might be the average yield according to Wisconsin agricultural statistics. We see that 8.5 pounds or 8.5 tons per acre of yield gives us about 73 pounds per acre removed through harvested material. If we assume a fertilizer rate of about 150, Um, that gives us about 64 pounds of leachable N. The one thing that we often neglect in irrigated regions is what might be coming from the irrigation water. So it's important to kind of take a look at that as well. And if we assume, 18 milligrams per liter in somebody's irrigation well, and we assume 10 inches of irrigation was added during the growing season, that adds an additional 41 pounds per acre, and we get this leachable N of about 104 pounds. If we were to change the fertilizer, say we only applied 130 pounds, we'd see that that would decrease that pool or the amount of leachable N. If we increased it, it would obviously increase the amount of leachable N. If we go back to 150 for fertilizer, we could also play around with the yield. And let's say, it was a abnormally cold year. We didn't get higher or as high of a yield, and we only got 7 tons per acre. Because we're removing less, there's more potential for leaching. If we get a year where we get really good yield and 11 tons per acre, we're removing more nitrogen from that system, we're going to get less leachable N. So this is just a simple way to think about, the groundwater contribution or groundwater impacts from these various practices. I'm going to go back to the presentation here. And did it flip back, John? Thanks. So if we use that example and we put it into context of kind of typical crops in this region, and we look at kind of the average yields that we might expect for these crops, and we look at ranges of fertilizers, what we see is that budget, and the leachable nitrogen is on the far right of this table. And you can see kind of a gradient. Crops like potato and sweet corn tend to leach the most. Snap beans, we had to use kind of estimates. Matt Ruark was really kind to give me some guidance in terms of how to approach legumes with a nitrogen budget like this, and his suggestion of using fertilizer rates for non-nadulating varieties of legumes is one way that we can estimate kind of leaching losses that might be associated with legumes. So looking at the fertilizer inputs, the outputs, we can kind of see estimates for these various crops as we allow fertilizer to vary. We could also do the same thing if we focus on sweet corn. The first line shows what happens if we allow the fertilizer rate to vary. The next line illustrates if we keep fertilizer set and we allow the yield to vary, it shows what impact that has on the leachable N. So we get this range for these different crops. And for sweet corn, anywhere between about 80 and 120 seems to be what the data using the simple nitrogen budget would suggest. And is that accurate? It probably seems like a lot for some people. Again, knowing that the irrigation is included in this, that might add or cause people to think a little bit about this a little bit harder in terms of what contribution that irrigation water has on this equation. So I think some people are often surprised it's that high, but if we start including all the inputs, I think we can see numbers that do look like this. How does it compare to the groundwater though? And that's where we can look at data that we've been collecting over the past 5-6 years from some of these systems in central Wisconsin. So this is one particular field where I've got annual data where I've tried to estimate the impact of the cropping system on groundwater quality for individual years. And what you see is that from this method where we sample the water table at a very good spatial representation, it's showing the box plot for nitrate concentrations that we can assign to a particular crop. And potato years, multiple years of potato, we're getting about 40 milligrams per liter. The 1 year of sweet corn we have about 30 milligrams per liter. Field corn, is around 20, maybe slightly above 20 milligrams per liter. And if we look at the 1 year where we had peas followed by pearl millet, we're getting down, around 10 or slightly less than 10 milligrams per liter. So this starts to line up with the simple budget that we showed in the previous slides. And if we again pick on the sweet corn, which is in red, 30 milligrams per liter, does that make sense to us? And if we look at relating nitrate concentration to inches of recharge, in that system, we might expect about 15 inches of recharge. And if we assume 30 milligrams per liter in our groundwater, and we use this table or we do this calculation, what that 30 milligrams per liter from 15 inches of recharge would suggest is that we would have had to have leached about 100 pounds of nitrogen from that field. And again, that lines up really closely with what we estimated using that simple budget. So I think those simple budgets can be really valuable tools for helping us understand, which particular crops we might be losing nitrogen from. This is just another experiment we did in that same field, looking at when is that leaching occurring. I'm not going to get into a lot of details, but I do want to show some of the results of that for the individual periods. So for an individual period, if we have the volume of water, if we have the concentration of nitrate, we can determine the mass or the amount of nitrate loss for an individual period. And an individual period might be about a 2-week period between sampling. And what we see is that a significant amount of nitrogen is lost outside the growing season. So in these pictures, it's showing the cumulative nitrate loss for each individual year. And by year, I mean a planting date to planting date of the following year's crop. That's what I would consider to be what I'd call a leaching year. What impact is one crop having on the annual leaching losses from that field? And again, the dashed green line represents planting date. The red line represents harvest date. And we are losing nitrogen during the growing season. But in some years, it's might be surprising to people the amount of nitrogen that's being lost outside the growing season. And if we're ignoring those time periods outside the growing season, we're ignoring opportunities to try and impact or minimize nitrate losses to groundwater. This is just a conceptual model kind of highlighting everything we've talked about here, that, economic optimal nitrogen rates or nitrogen fertilizer rates vary with crop. So the type of crop we're growing can kind of be used, these simple nitrogen budgets can kind of be used to estimate or predict which crops are going to have the greatest impacts. And then obviously areas with susceptible soils or geology, those impacts are going to be magnified or exacerbated. The question everybody's talking about is what to do about it. And that's where I think we still need more data, is what other practices can we realistically implement that would maintain profitability, but have meaningful impacts on groundwater quality. This is just a summary table from Iowa, so take it with a grain of salt, because it might not all be appropriate for central Wisconsin, but I think it's good because it shows, we can start quantifying the impact of these practices and then applying those to particular situations, especially if we start thinking about this as a challenge that lasts 365 days a year, not just something that we have to think about during the growing season. So particular interest on this slide would be, what would be the impact of cover crops on helping to manage or contribute to this problem? What would the impact of more diverse rotations be? If we look at the cropping systems now, can we add lower nitrogen intensive cropping systems to help improve this? In a year where we're growing potato, maybe we have limited impact. But if we take field corn out of a rotation and replace it with a lower nitrogen requiring crop, what impact would that have on this piece of the puzzle? So I'm going to leave it with this slide, which is our nitrate opportunities. I think it's going to be difficult in central Wisconsin to say we're going to go from 40 milligrams per liter, 30 milligrams per liter to zero. That would be a significant challenge. But I do believe we could start talking about going from 40 or 30 down to 20 or 15, and that would have meaningful, measurable impact. And I do think it's achievable if we start thinking about the whole nitrogen system here. And that means looking at ways that we can increase nitrogen storage. And by nitrogen storage, I mean temporary storage of nitrogen in that soil profile, where we learn to subsequently credit that nitrogen to future years. It's looking at diversification of crop rotations as a way to reduce overall nitrogen inputs. It's talking about things like increasing nitrogen use efficiency. So if we're able to achieve higher yields with the same amount of nitrogen, or grow the same yields with less nitrogen, those are ways to increase efficiency. So these are all things that I think are worth exploring, and I think are exciting opportunities for moving forward. And I'll leave it at that. And Jed, if we do have time for questions, I'd be happy to take any questions that have come up.
Yeah, thank you very much, Kevin, for your very clear presentation. In fact, it may be so clear that we haven't had questions entered at this point. I'll ask one final time if anybody, oh, we do have one. Thank you, Christy Angelo. Why do you think nitrogen leaching increases so much after the end of the growing season? A great question.
That is a good question, and it's it depends on the year. It's not so much that I think of it as nitrogen leaching increasing. It's more how much nitrogen is left over from that budget. Um, how much nitrogen is left over in that budget, is going to determine how much leaches after or outside that growing season. When we get precipitation is going to determine when that nitrogen leaches. So if we have a lot of nitrogen after the growing season, and it's really wet fall, we might see that nitrogen leaching that fall. If we have a dry fall, but we have a really wet or a lot of snow melt in spring, we might see that nitrogen leaching the following spring. So it's really dependent on how much nitrogen remains after you're growing that crop, and then how much rainfall we have to push that nitrogen through the soil profile. But in sandy soils, I think, whatever's left over, we have plenty of rain in most years that it's going to leach sometime between harvest and planting of the following year before you start adding nitrogen again. So I don't
Right.
know if that helped clarify, but that's how I tend to think of it.
Right. Yep. Thank you. We have a second question from Dan. Do you think N application timing will have a greater impact at more northern latitudes compared to the Iowa model presented?
Um, yeah, I mean, timing is important for building efficiency. So when you look at the Iowa nutrient reduction strategy, the studies or the literature review they did on timing basically showed, maybe less than 10% effectiveness, with a wide range of standard deviation. And that wide range of standard deviation makes sense if we consider timing during a dry year probably has very little impact on getting nitrogen into that crop. But timing during a really wet year, if you put half your nitrogen out, you get a 3-inch rainstorm, and then you apply the other half out after that rainstorm, there's a lot more potential for it to be more efficient with that nitrogen. Um, so the timing, is going to be relative to when rainfalls occur, and that's going to be highly variable from year to year. Uh, timing is one piece of that equation, amount is another. So if you truly are more efficient with timing being a way to get more nitrogen into the plant, then you should be able to actually decrease, nitrogen recommendations. That would be the goal, is to develop timing recommendations that allow you to, if they truly increase efficiency, then they should allow you to cut back on how much nitrogen you're applying. If you're not getting increased yields from that timing, um, you might reduce or decrease leaching losses during the growing season, but that nitrogen's still going to be left over after harvest and potentially available to leach. So I'm maybe talking out loud or talking through things in circles here, but I think that's definitely something I'd be interested in discussing more. If I'm not explaining something clearly, or I'm not thinking about your question
Right.
very clearly.
Right. And we can certainly have follow up after the meeting also. I have one question for you also related to the Iowa nutrient reduction strategy in the chart that shows the likelihood of change. And in the rye cover crop in particular, I notice a potential for 31% reduction, but a standard deviation of 29%. There we go in the middle of the chart. As compared to the oats, do you have an idea why that is that way?
Yeah, and I always hesitate whether to show this slide or not. And if you dig into their research, I think they summarize very few studies. So I suspect, if there were more research on these topics as it related to water quality, these error bars might be a little bit tighter. The reduction potential might be slightly different. Um, I just like this slide because it shows kind of relative effectiveness. These numbers were from cover crop treatments in states further south, so
Right.
I'm not sure we could expect the same potential here in Wisconsin. But if we can use cover crops, and cover crops are able to accumulate significant biomass, then I do think we can be cautiously optimistic that that would be one strategy to look at this, or ways to look at this outside the growing season, in terms of that temporary nitrogen storage and then subsequent crediting to additional years crops.
Right. Thank you. So Charlie asks a question, and then we'll move on. We have a couple actually. We did see less spring soil N, Charlie points out, following a sweet corn crop if we planted rye after sweet corn in Waseca, as Charlie outlined in his presentation last week.
Thanks for that comment.
Yeah, and Jason points out the Iowa nutrient reduction strategy is based on a lit review. The range is related to how much growth will occur of the rye cover crop. Decent growth of rye cover crops can reduce nitrate leaching and export out of tile drains by 50%. And I was also wondering if, as in most cover crop studies, we often see a wide range of reported cover and biomass and such, depending on the season, type of rye, whether it's winter killed or a cereal rye and such. So I suspect there's a fair amount of variability also in how the research is conducted and where it's conducted, as you pointed out.
Yeah, thanks, Jason, for that much more eloquent way of explaining that. And I see there's yeah, John looks like he direct messaged, but had a comment or a question. And yeah, just the fact that after the growings, and we generally don't anything growing in the field, and that's missed opportunities to try and scavenge and hold on to some of that nitrogen. So I'm excited about opportunities moving forward for both cover crops, maybe interplanting in some of these fields, to try and look at this issue from different perspectives.
Right. Agreed. Great. Well, thank you very much, as usual, Kevin, for a very clear presentation. It's much appreciated.